In our last lecture, we were talking about how we can use the oxidation reduction process to balance what we call oxidation reduction equations, or redox is the way that we sometimes refer to them as an abbreviated form. And we had started looking at an example equation for balancing processes, and so we'll start back at the beginning here of stepwise what we had talked about up to that point relative to this one particular chemical reaction. Dichromate, Cr2O7 with a 2- charge, reacting with iron 2, iron with a +2 charge, to give us chromium 3+ and iron 3+. And as I indicated in that starting of this one the other day, that we can add hydrogen ions, water, and electrons as needed to end up with a balanced equation. The technique that we are starting to develop is called the charge balance method. So not only are we going to balance the atoms, that's the mass part, but each reaction must also be balanced in terms of charge. Okay? So we break the equation down then into two parts. An oxidation part, which in this particular case is the iron, going from the 2+ to the +3. It's increasing in oxidation number, so that's the oxidation reaction. And the other reaction, the dichromate going to chromium 3, which must be the reduction equation. All right. We first started then looking at iron 2+, and we just have one iron atom and one iron atom, so the atoms or the mass part is already balanced in this case. We don't have to do anything with the mass. But the charge isn't balanced. On this side we have a net charge of 2+, and on this side we have a net charge of 3+. And we're going to need to add electrons. That's the only other thing that we can add. We can add electrons then to balance the charge, keeping in mind an electron is a -1 species. So we concluded that if we were to add now an electron to this side, we would have the 3+ plus a minus, leaving us with a +2 charge on the product side, and on the reactant side we had a +2 charge. We now have the same charge on both sides of the equation, and so we now have balanced the atoms, one iron atom on each side, and we now have balanced the charge +2 on each side. All right? So we have balanced the first, as we call it, half reaction, and this is the oxidation half reaction. Iron has increased in charge. Iron 2 has lost an electron. So by both of our definitions, this is an oxidation process that has occurred. Now we turn to the reduction, the other half part of the chemical equation, and this is the dichromate. Now Cr2O7 2- going to Cr3+. Again, we start first by looking at balancing the atoms. In this case, we note that we had 2 chromiums over here, and we're only showing 1 here. So our very first thing that we're going to do now is we're going to put in a 2 in front of the chromium. So we now have 2 chromiums and 2 chromiums. So the chromium atoms are now balanced. Now, the oxygens aren't balanced. On this side we have 7 oxygens, and on this side we have no oxygens. And in the charge balance method, the technique that we use is that we add 1 molecule of water for each oxygen that we are short. To whatever side is short oxygens, we add 1 molecule of water for each oxygen that we are short. So we're short 7 oxygens on the product side. So our next step then will be to add the 7 molecules of water to the right-hand side of the equation. When we do that, we now have balanced all of the atoms. 2 chromiums, 7 oxygen, 7 oxygen. But when we added the 7 waters, of course, we now have added 14 hydrogens to this side. And these are hydrogens with a +1 charge because they're combined with the oxygen. So we must now add 14 hydrogen ions to the reactant side in order to balance the hydrogens. So at this point we now have 2 chromiums, 7 oxygens, and 14 hydrogens on each side. It's important, very important as a matter of fact, that we show these hydrogens that we've added as +1 ions. That's very important when we do the charge part of the balancing of this equation. All right, so now let's take a look. What do we have charge-wise on the 2 sides of the equation? Water is 0. So we have 2 times the 3 plus. We have a +6 total charge on the product side. How much charge do we have over here? Well, we have a -2 ion and 14 hydrogens, and so we would have then +12 total charge on the reactant side. So, keeping in mind now that to balance the charge we add electrons, how are we going to get the 2 sides equal in charge? We will need to add 6 negatives to this side. We can't add positives. We can't add protons. All we can add are electrons. So we could add 6 negatives to this side because +12 minus 6 would leave us with a +6 charge. And that's exactly what we do then. We now add the 6 electrons to this side. And so now we have a net charge of +6 over here and a +6 over here. We've now balanced the charge. Now, once we have done our 2 half reactions, we did the oxidation half reaction, we've now done the reduction half reaction and have them balanced, we're ready to combine the 2. However, when we combine the 2, the electrons lost in oxidation has to be equal to the electrons gained in reduction. Well, when we go back up here and look at our first half reaction that we did, the oxidation part, we see that we had only 1 electron involved. When we looked at our balanced reduction equation down here, we had 6 that were gained. Well, if the dichromate is going to gain 6, the irons had to give up 6. Now, we don't want to unbalance the equation, however, because we already had it balanced. So, what do? We're going to take now, this is our 1 balanced equation there, and let me go ahead and kind of sneak those +6s out now because that was just for our bookkeeping part. Okay, so we have a balanced equation there. We're going to multiply the other one through by 6. If we put 6 irons and 6 irons and 6 electrons, we haven't changed the balance. But now we can see that the 6 electrons gained by this one are equal to the 6 electrons lost by that. We're now ready to add together, to combine our 2 half reactions. And the final result then, the final balanced reaction, is then 1 dichromate plus 14 hydrogen ions plus 6 Fe2 pluses gives 2 chromium 3, 6 iron 3s, and 7 molecules of water. And seeing that's a little light there, let me just go ahead and rewrite it right under here so we're sure that we see it all. Dichromate ion plus 14 hydrogen ions plus 6 iron 2 pluses yields 2 chromium 3 plus plus 6 Fe3 plus 7 H2Os. Now, one should double check their final equation, check it for both the fact that atoms are balanced and charge is balanced. Looking at atoms quickly, we have 2 chromiums and 2 chromiums. We have 7 oxygens and 7 oxygens, 14 hydrogens, 7 times 2 is 14, 6 iron, 6 iron. So we've got all the atoms balanced. Total charge on this side is a plus 14 and a plus 12, so that would be a total charge of positive 26 minus the 2, so we have a plus 24 charge on this side. On this side over here we have 2 times plus 3, that would be plus 6. 6 times plus 3, that would be plus 18. Positive 18, positive 6 would give us plus 24. So, in an oxidation reduction equation, not only do the atoms have to balance, but the charge must also balance. Yes?
When you first added water, you added the 7 H2Os, and you have a positive on that. How come you didn't use that in your balances?
No, I just pointed this out, that these hydrogens aren't neutral atoms, that charge has nothing to do with adding up the charge. So I'm sorry if I made that sound that way. I just put it there so that when we wrote the H's over here, we were sure that we put them in as hydrogen pluses, not hydrogen zeros. Okay. This little plus here was just my note to remind you that the hydrogen there isn't a hydrogen atom, it's a hydrogen with a plus charge. Okay, so good question. All right, any other questions on that one? Actually, that's about the most messy, complicated one we probably will encounter. So we start with the most difficult and then go on and look at ones that are easier. So if we can handle that, we should be able to do the easy ones. Well, let's take a look. Here's another chemical reaction. Copper reacting with nitrate to give us copper 2 plus and NO. And we have, again, 2 parts that we're going to need to look at. We're going to need to look at this change, and we're going to need to look at this change. So we look for 2 half reactions. So I'm starting here first of all with the copper to the copper 2 plus. We can already see that the atoms are balanced. So the only thing that we have to balance in this particular half reaction would be the charge. And we see that on the left-hand side we have a net charge of 0. On the right-hand side we have a charge of plus 2. And so how are we going to get the charges equal? Going to add 2 negatives to the product side. So my next step is going to be to show Cu goes to Cu 2 plus 2 electrons. And that's the end. That's balanced. All right, just as a little review, is this the oxidation reaction or is this the reduction reaction? Heard somebody say? Oxidation, that's correct. We've got an increase in charge from copper 0 to copper 2 plus. We have a loss of electrons. This carbon atom is losing those electrons to something. So loss of electrons, oxidation, or gain in charge number, oxidation. So either way we want to look at it. We now turn to the other half reaction. And the first thing is we notice that the nitrogens are balanced. However, we have 3 oxygens on this side and only 1 oxygen on this side. So we're 2 oxygens deficient. And so the next step is we're going to take now, we're going to add 2 molecules of water to this side. That's to get 3 oxygens on the right. When I did that, however, of course, we note that I've now added 4 hydrogens, keeping in mind that they're charged hydrogens, they're not hydrogen atoms. And so, because I did that, I must add 4 H pluses to this side. I added the water to get the oxygens. I now need to add the hydrogens to get the hydrogens balanced from the water. And you might ask, well, that seems kind of dumb. Why don't we just add an oxygen? Well, we can't just add oxygens. There are no such things as free-running O2- ions running around that we can throw in. So we have to put it in a form that is realistic. And the realistic form is to put it in the form of water. Okay? Now, atoms are balanced. The last thing to do is check the charge. On this side, we have 4 pluses and a -1. We have a charge of 3 plus on this side. Over here we have a 0 and a 0. These are molecules, neutral molecules, so the total charge on this side is 0. And so again we ask the question, what can we do to balance the two sides? And hopefully the obvious thing is we need to add 3 minuses to this side over here. And so we're going to add, and I'll sneak it in right here, plus 3 electrons. So that now, with the added 3 electrons, we will be 0 and 0 for the two sides. Now, once we have accomplished that, this one was balanced, and this one is now balanced. I'm ready to add the 2 half reactions together to get a total equation. And when I do that, I must keep in mind electrons lost and electrons gained must be the same. Well, they obviously aren't. I've got 2 lost and 3 gained. So the question becomes, what is the least common number to 2 and 3? 6, I heard somebody say. That's correct. So what I'm going to do is I'm going to adjust both of these half reactions so that they will have 6 electrons in them. To get this one to 6, then I'm going to go ahead and multiply through by 3. So I'll write it right down here. 3 Cu forms 3 Cu2 plus 6 electrons. I'm going to multiply this equation through now by 2, and I'll rewrite it down below here. So we'll have 8 H pluses plus 2 NO3 minus plus 6 electrons yields 2 NO plus 4 H2Os. When I have done that, I am now ready to combine the 2 equations because I can now cancel the electrons out. Once we're able to do that, we're ready to add them together. So the total balanced equation then would be written as 8H plus 2 nitrates ions plus 3 coppers yield 3 copper 2 plus ions plus 2, whoops, I forgot the 2 in there. Do it that way. 2 NOs plus 4 H2O. Now again, the equation should be balanced in terms of atoms and charge. If we look at atoms quickly, 8 hydrogens, 4 times 2, 8 hydrogens. 2 nitrogens, 2 nitrogens. 6 oxygens. There's 4 there and 2 here, so that's balanced. 3 copper, 3 copper. Charge-wise, on this side we have plus 8 and then 2 minuses. So we have a net charge on this side of positive 6. Over here we have 3 times 2 plus, NO, which is 0, water, which is 0, we have plus 6 over there. So it's now a total balanced oxidation reduction equation. Any questions on that? Yes, question.
No matter what order you
Right.
Does it matter?
No. The question was, does it make any difference what order we write the reactants and products? And the answer is no. Makes no difference whatsoever. Okay? All right, let's try one more here. We'll see if we can go just a little bit faster this time. We have permanganate. I think there must be something wrong with the mirror in this thing because I can't seem to get a whole big very area that's focused, so I apologize for that. We'll try to work in the best area. We have permanganate reacting with tin 2 to give manganese 2 and tin 4. And so this is one of our changes that's occurring, and this is the other change that's occurring. So those are our two half reactions that we're going to look at. So let's start here with the permanganate. And it doesn't make any difference which one we do first. I just usually pick whichever one happens to show up first in the equation, and so permanganate here is the one we're going to go ahead and start with. Now, we look for atoms. We see that we have one manganese on both sides, so the atoms are already balanced. We don't need to do anything more with that. However, the oxygens aren't balanced. We note we have 4 oxygens on this side. We have none on this side. And so we will go ahead now and add 4 molecules of water to the right-hand side. When we did that, of course, we've now added 8 hydrogens, so we need to come back over here then and add 8 H pluses to the left-hand side so that we have the hydrogens balanced. At this point, the atoms are balanced, and our last step now is going to be to balance the charge. So we need to check. On this side, we have 8 pluses and 1 minus. So we have a net charge on this side of plus 7. Over here, we have 0 for the waters. We have a plus 2. So we now need to add the appropriate number of electrons, and to change then, hopefully, by this point, it would seem obvious that what we will need to do is to add 5 negatives, 5 electrons to this side. By adding the 5 negatives, we now have reduced the charge to plus 2, and so both sides are now positive 2, and we have a balanced half reaction. Now, the other half reaction is going to be pretty quick because all we have to do is balance the charge because the atoms are already balanced. And so, in this particular case, looking at it, we have a plus 2 on this side and a plus 4. Again, as I say, I hope at this point we can recognize quickly that what we will need to do is merely add 2 negatives to the product side. Now we're ready to combine the 2 half equations. We notice that we have 2 electrons lost and 5 electrons gained. And so the question would be, what is the least common number to 2 and 5? Heard somebody say 10. So 10 electrons is what we need to have both reactions achieving. So I'm going to go ahead and multiply this one through by 2 up here, and I'll write it right in between here. So we have 16 H pluses plus 2 MnO4 minus plus 10 electrons yields 2 Mn2 plus 8 H2Os. And we need to multiply this other one through by 5. So I'll do that, and I'll write it right up underneath the other equation there. So we're going to have 5 Sn2 yields 5 Sn4 plus 10 electrons. Now once we've done that, we note that now 10 electrons are gained and 10 electrons are lost, and we're now ready to combine the two equations. So we can now add together, and so our final balanced equation is 16H pluses plus 2 MnO4 minus plus 5SN2 plus yields 5SN4 plus 2 Mn2 plus 8 H2Os. And again, one nice thing about balancing oxidation reduction equations is that we immediately can check our answer to see if it's right. Because if both atoms and charge check, then we know that we have balanced it properly. Well, checking quickly, 16 hydrogens on both sides, 2 manganese on both sides, 8 oxygens over here, 8 oxygens over there, 5 tin and 5 tin, so the atoms are balanced. Charge-wise on this side, we have plus 16 and then plus 10, so that's plus 26, minus the 2, we have a plus 24 charge on the reactant side. Over here we have 5 times plus 4, that would be plus 20, and 2 times a plus 2, that would be 4, and 20 plus the 4, positive 24, and our two sides check. All right? Now, any questions on that? So far, each of the problems we've looked at have been in what we call the form of an ionic equation, containing only those particles that actually undergo chemical processes. And we didn't show the ions that we refer to as spectator ions. If you recall, earlier in the year, we talked about writing ionic equations or net ionic equations, which then didn't include those ions that aren't really involved in the chemical process. But we can also balance oxidation reduction equations if they're written as a molecular equation rather than as an ionic equation. And we use the same process that we did before. The only difference is we may have to do a little bit more bookkeeping part when we get done, because we won't have balances necessarily on those things that are only there as spectator species. All right? Well, let's take a look. First of all, we're going to have to figure out of all of this mess, what things are actually changing. So if we take a quick scan here, we see potassium here and potassium there. In each case, it's combined, and it's always going to be a +1. That's the rule of the 1A metals. Over here we have permanganate, MnO4, and over here it's MnCl2. Well, that sort of looks like maybe something did happen to it, but we would need to check. What would the charge be on the manganese in this compound here? That's why we looked at how we went about assigning the oxidation numbers earlier in the chapter. We would have oxygen here is a -2, times 4 would be a -8, and potassium is a +1, and it's just one of them. And the whole compound has to be 0, so we would determine that the manganese must have been a +7 over here. Over here, chlorine is a -1, and 2 of those would be -2, meaning that the manganese over here is a +2. So we see that the manganese has undergone a change. So that's one of the reactions that we're going to need to write. So let's go ahead and put it down here. We're going to write KMnO4 becomes MnCl2. So we've identified that as one of the changes. Did hydrogen change? No, it's +1 both cases. Did chlorine change? No, it's -1 every place it appears. That hydrogen obviously didn't change. How about sulfur? Well, over here it's an element, and what's the charge on any element? 0, I heard somebody say. That's correct. That's one of the rules we looked at the other day. The charge on any element is 0. Well, if it's combined with something over here, it obviously can't be 0. It has to have a charge to be combined. And actually the charge here determining it, we know hydrogen is a +1. That's 2 pluses. And so the sulfur must therefore be 2 minus. So we see the sulfur is changing from 2 minus to O. And so there's my other thing that's actually involved in the oxidation reduction process. So we'll have a second half reaction that will involve H2S becoming S. So those are the two changes we have to write balances for. Well, let's go ahead and start with this one then. We have 1 potassium on this side and none on this side, so let's add 1 potassium over here. We have 1 manganese over here and we have 1 there, so that's all right. We don't need to worry about that. We have 4 oxygens over here, don't have any over here, so we'll need to add 4 molecules of water. When I did that, don't forget now I need to go back and add 8 hydrogen ions to the other side. And we've got 2 chlorines over here and none on this side, so we'll throw a couple of chloride ions over here. Not carbons, chlorides. Okay? So now we should have all of the atoms balanced. 8 hydrogens, 1 potassium, 1 manganese, 4 oxygens, 2 chlorines. So the atoms are all balanced. Now the last thing then is to check the charge. On this side we have a +8 and a -2, so we have a total charge of +6. On this side we have a total charge of +1. Everything else is a molecule. And so to get balance, again hopefully at this point, we would recognize that what we will need to do is we will need to add, and I didn't give myself a whole lot of room to do that, we'll just kind of sneak it in here, +5 electrons to the reactant side. So the 5 negatives with the +6 is now going to give me a final charge of +1, and so now the 2 charges are equal, and we're done with that. We now come down to the other one, and that one's starting to look pretty easy. We have 1 sulfur on each side, 2 hydrogens over here, so we'll throw a couple of hydrogens over there, and the atoms are already balanced. Only thing we need to worry about then is balancing the charge. And we see that net charge on this side is 0, the net charge on this side is a +2, and so therefore to get the charge equal we will add 2 electrons to this side. Now we had 2 electrons lost, we had 5 electrons gained, and so therefore again the least common number to the 2 would be 10. So we need to multiply the first equation through here by 2 and the second equation here through by 5. Now because of space I'm not going to bother to write the electrons in, because 2 times this is going to give me the 10, 5 times that one's going to give me 10. They're going to cancel out. So I'm merely going to write down at this moment then what I would have of the actual species at this point. So I have 2 times 8. I have then 16 H pluses plus 2 KMnO4s plus 4 Cl minus plus 5 H2S. So I've multiplied the reactant side by 2 for the first one and the reactant side by 5 for the second one, and combined everything that was on the reactant side. On the product side, multiplying through by 2 over here, we're going to have, and I can see what we're going to have here is going to take more room. I'm going to draw a long arrow and start it right down here for the reactants. We're going to have 2 MnCl2s plus 2 K pluses plus 8 waters plus, now we're going to go to this one, plus 5 sulfurs. Should have started over further yet. Plus 2 times 5, 10 H pluses. What a mess. Now, at this point, we could check charge and balance. I'm fairly comfortable we have it right, so we won't bother to do that. But what I want to do now is I want to go back to our original equation, if we can see both, and put in the numbers up here now that should finally balance that equation. And I'm going to start here, first of all, with the molecular species. I had 2 KMNO4s, so I'm going to put a 2 right here. I had 5 H2S's, so I'm going to put a 5 up there. I'm only writing down the things that are molecular. I had 2 manganese chlorides, so I'll put a 2 there. That'll take care of that one. I have 8 molecules of water. That's good, so we'll put down an 8 for that. All right. And, 5 sulfurs from this one, so we'll put a 5 down there. Now, we can kind of scratch those out because we've done all of that part. That's gone, that's gone, that's gone, this is gone, this is gone. Now, it tells me left, I have to have 16 hydrogen ions, or 16 H pluses, someplace on the reactant side. So I go up here and I look. Notice that we already have 10 here. We need 16, so I will put a 6 there for bookkeeping. I had 10, I need to add 6 more. I can't change the ones that were the molecular ones, I can't change because they were balanced by oxidation reduction. Okay? All this says is that I have to have 16 H pluses someplace on the reactant side. Those 10 are tied to the thing that's changing, sulfur. So we can't do anything with that number, but we can put a 6 there. Now, when we did that, we now have 6 chloride ions. What does it say? It says that we need at least 4 chloride ions. Do we have 4 chloride ions and 6 HCl's? Yes, we do. We have a couple of extras. One might wonder, why do we have a couple of extras? Well, we'll see here in a moment. But we've got all of those, and we have all of those taken care of. And we even had a couple of extras. Now we go over to the product side, and we need 2 K pluses. And we have only one place that potassium appears, so we're going to have to write a 2 in front of that. And that gets rid of our 2 K pluses. We've taken care of that. And finally, it says that we have to have some places showing 10 H pluses. Well, we come back here, we have 8 waters. That's 16 H pluses right there. So certainly 16 would give us 10 that we needed for the oxidation reduction. So that's gone. All right, now, the question is, do we have everything balanced at this point? Back to our molecular equation. And we check. We had 2 potassiums, 2 potassiums, 2 manganese, 2 manganese, 8 oxygens, 8 oxygens, 6 hydrogens, plus 5 is 16 hydrogens. 8 times 2 is 16 hydrogens. 6 chlorines. We had 2 there, and we have 2 times 2 is 4 there. We have 6 chlorines on this side. We have 5 sulfurs. We have 5 sulfurs. Everything was 0 because they were all compounds. So the charge is already going to balance no matter what we put number-wise, but we have now balanced also every atom in there. So we now have a total charge and mass balanced equation. I'll get a question in just one second. If I had given you that equation to try to do by inspection, by bookkeeping, chances are very good you'd have never got to the answer. Because so many times when you have things that appear here, it only appears in one compound, it appears in two over here. Hydrogen appears in two compounds over here, but only one over here. So if you make a change here to adjust the sulfur, it messes up the hydrogens, and so on. The only way that you could realistically balance that equation was to use the oxidation reduction balancing method. I had a question back there.
Yeah, on the last step that you did on the bottom, for some reason we did not use the 10 electrons on the right-hand side. I never showed up.
Let me see. The question was there some reason I didn't use 10 electrons on the right-hand side? I don't think that I wrote the 10 electrons on either side, because I think I said that we're going to multiply this one up here through by 2, and therefore we have 10 electrons, and I'm going to multiply this one through by 5, and we're going to have 10 electrons. And I said I wouldn't bother to write the electrons down because I could see that they're going to cancel out anyway. Okay? All right? Any other questions on balancing oxidation reduction equation? Now, oxidation reduction equations, or reactions I should say, can occur in a direct fashion, or we'll find that they can occur in an indirect fashion. This is a penny in a beaker. And to that penny being copper, I'm going to add some nitric acid. And after I add some nitric acid, in a little bit of time, I find that I have a whole bunch of reddish brown gas being evolved in that beaker. And the nitric acid, when I put it in, is colorless, and the nitric acid has become a dark blue-green in color. So obviously, a chemical reaction has been occurring. And actually, if we look at what has been occurring, we can show the reaction here is that the copper, which was metallic, has been oxidized to copper 2. Copper 2 ions in water are blue. If you've ever seen a copper sulfate solution, it's a blue solution. It's due to the copper ions that are interacting with water molecules give us the blue color. The nitrate, which was colorless, forms NO2 gas, nitrogen dioxide. And NO2 gas is a reddish brown colored gas. That's what we have here. Well, so obviously copper is losing electrons. It's lost a couple. And nitrogen in the nitrate has gained an electron to go from the +5 in the nitrate to the +4. So it's an oxidation reduction process. The thing in this particular oxidation reduction process is that the copper atoms are giving the electrons directly to the nitrate. The nitrate collides with a copper atom, the electron exchange occurs, and we get the products formed. But in our next lecture, looking at oxidation reduction reactions, we're going to look at indirect oxidation reduction chemistry, leading us to a discussion of what we call electrochemical cells. Today I'm talking with Dr. Jahnke, Professor of Chemistry and Head of the Chemistry Department. Dr. Jahnke, one of the topics that frequently comes up today in science education is how can we interest young girls in choosing careers in science? Could you explain a little bit how you became interested in science and when that occurred as far as for a possible career?
It started with my family, with my father and my mother. My mother is a registered nurse. My father is an outdoorsman, and he took me hunting and fishing and camping and got my interest in what makes things work. But probably as it grew on, it became teachers, and I had a high school teacher who took an interest in me and allowed me to explore and find out what I was most interested in. And what it boiled down to is I wanted to know the fundamental answers, and so that led me to chemistry.
Tammy, you and I, of course, have used our chemistry background to pursue a career in chemistry in the university academic level. I'm sure there are many other career paths that one can use a chemistry background in. In the next few moments, I'd like to spend some time exploring maybe some of those other possible career pathways. Could you identify possibly some places that we might find people with BS or BA degrees in chemistry where they might be employed?
You'd find them in chemical manufacturing. The petroleum industry hires a number of chemists. You'd see a chemist working in a quality control area, and that could be quality control with respect to food chemistry, with respect to pesticides, herbicides, agricultural chemistry. It could be a chemist working in a crime lab doing forensic chemistry. It could also be an environmental chemist working on environmental problems, whether it be air or water or soil chemistry. Also, the cosmetic industry hires a number of chemists. All the perfumes, all the cosmetics that we use are formulations that a chemist needs to get involved with, both in quality control and also in research and development.
Well, those are all very interesting career choices, of course, based on a full degree in chemistry. Are there any health-related careers that you can think of that at least use a strong chemistry background for their preparation?
Yes, absolutely. Medicine and dentistry are two obvious choices that students have with a chemistry major is going on to a professional school. Also, medical technology is a career option. Industrial hygienist, environmental health and safety officers. Any career in the health profession will require some basic knowledge of chemistry and of science to continue on in that career.
What about somebody that might have an interest in business, and could they possibly tie a career together using business and a chemistry background as well?
An opportunity there would be possibly in sales. They would have the knowledge to be able to explain their product and help in a way that a salesperson with a business degree might not be able to do that. And things like chemical supply firms, chemical equipment companies, pharmaceutical sales are looking for people who have a background in chemistry that can explain their product to others that might be interested. Another career option other than sales is technical writing, and looking at that background in chemistry and the writing skills and being able to explain to someone in a technical manual to do some technical writing, and that's another option for a chemist to take that might not be typical.
One of the areas, of course, that we're both involved in and deal with is education. Could you talk a little bit about some of the career options that might exist for people that would like to become involved in chemical education as a career?
Well, first of all, it would involve teaching in the elementary, middle school, or high school. Just recently I was at a conference where they said that they were looking for over 70 middle school and high school teachers, and we've only had 5 or 6 graduates in that area from this university. And so those people are finding jobs readily. And so high school and middle school teaching is one obvious choice. But then going on at the junior college level, at the university level, there are positions in all areas of chemistry for teaching.
I've been talking today with Dr. Jahnke about careers based on chemistry backgrounds. It appears that there's certainly many opportunities for people with that type of background for career options. Dr. Jahnke, I'm sure that if people were interested in pursuing the question further, they could contact you at the chemistry department and you could share some of that information with them. I do want to thank you for taking time today to share some of your ideas on careers in chemistry with me and the students in my class. Thank you very much.
Thank you.